Hi everyone, good to meet you. Today I'm going to talk about a new little sort of mini open source project we have worked on with one of my colleagues at Google called Coordax, which brings coordinate axes to JAX. Okay. Um, so first, why JAX? I'll give the little JAX pitch. But for those of you who work on sort of computational modeling or simulation, so JAX is a tool that Google's developed for. We use it to train the largest scale like AI models, which are really large scale simulations. It's also just a really great way to write high performance code in a pretty straightforward way. I mean, you can get it's like the speed of Fortran sort of and more using in Python. And you have all these other like really powerful features that we use for modeling. Things like JIT compilation, easy support for multiple GPUs, sort of auto vectorization and automatic differentiation. So I think it's just all just a great tool in general. It's been used for some pieces of sort of Earth system modeling codes. There's this Veris Ocean model, and then this Neural GCM, which is a project that my team has worked on, which is like a hybrid AI and physics-based atmospheric model. Okay, but we love labels, of course. I think all of us we're all Xarray fans, but Xarray, unfortunately, was designed for a slightly different use case. So I think Xarray, I mean, I can speak to this, I guess, was designed around analytics use cases, and so some of its features are not quite the right fit for high performance simulations. And I'll mention a few. So there's some of these unhelpful features. One example is automatic alignment. I think maybe even controversial if this is useful for analytics, to be honest, but especially unhelpful in simulations if you have slightly different grids and they try to like automatically match up the labels. You'd rather just get an error. In Xarray, we sort of skip missing values by default in most operations, especially like aggregations. That's like a little slower than necessary and like not something you want in a simulation. And there are just other kind of, again, challenges of using with Xarray. I'll mention a few. One is there's the overhead of everything happening in Python, which is interpreted, and that can be a little slow compared to compile code. It's a little painful to wrap code that's outside of the Xarray ecosystem that's not written with labels. And there also isn't support for sort of more complex coordinate systems, like on where you need to keep track of metadata, like something on a cell face versus a cell versus a cell center. Anyway, so all these problems actually Coordax solves. So let me tell you about how Coordax works. So it's kind of an interesting model. It is the main difference with Coordax versus Xarray is that Coordax arrays dimension names are optional. And it's built around these three methods: CMAP, tag, and untag. CMAP is what turns operations that unlabeled operations into labeled operations. Tag labels dimensions and untag unlabeled dimensions. And the way that CMAP is defined is that it operates only over unlabeled dimensions. So if you want to do something like apply a NumPy function like mpdiff over a field, you would a Coordax field, you'd make it kind of like an Xarray data array. You're going to first untag a dimension. You'll untag x. Now it has none for unnamed. Then you'll CMAP this function you're transforming here. It says mpdiff, and that it remains unnamed. It has a different shape now. And then if you want to give it a new dimension name, you just tag it. So we'll add x prime. So this is kind of like what it looks like to write stuff in Coordax. Of course, in practice, you would write this. You'd kind of write this all kind of in line, probably in one line instead of breaking out. It's kind of the equivalent in Xarray is apply ufunc, but CMAP is kind of like the supercharged version of apply ufunc. And this is kind of the contrast here. There's, I mean, of course, it's a bit more succinct. That's nice. The biggest difference is speed. Because it's in JAX, we can remove literally all Python overhead from this operation, including, and we can sort of do this like automatic vectorization as well with also no Python overhead. So it's like extremely sort of high performance wrapping, and it's sort of very low on verbosity. Of course, if you're comparing, I mean, it's helpful. I mean, Xarray of course does have like diff built in, for example. So it is not maybe not 100% fair here, but I mean, I think it speaks to the extensibility. If you look at, this is a kind of comparison of syntax here. There's a lot of stuff that's kind of similar in Coordax and JAX. They both have broadcasting arithmetic, and you can sort of a handful sort of built-in operations for kind of reordering dimensions. Now, if you want to implement functionality. We've implemented very little in Coordax, which I think is kind of one of the interesting things about the project. Is it for mean, for example, is just CMAP mean. And that's because this tag and untag paradigm is actually very powerful. And similarly, say for like stacking array dimensions, you just CMAP Jax NumPy stack. We might eventually build in aliases for these to make it a little bit more convenient as a shortcut, but we really like this. It's like a very nice sort of building block for labeled array operations. It's a very small core. And then lastly, of course, you can kind of easily go back and forth to Xarray and from Xarray with Coordax. So for things like we're probably not going to build in like plotting or like Xarray, for example. And then the last thing I'll speak, the feature we found really powerful for simulations is support for custom coordinate objects. And so Coordax has this pretty minimal API that you can define. This is like the whole implementation of a very simple coordinate class where you define a shape and dimensions. And now you have an object that propagates along with your labeled array operations. And this is, I think, really handy for sort of, again, for like more complex coordinate systems where you really want to of course, you have this object. You can add whatever methods you want on this thing. So if you want to add a spherical harmonic coefficients, you'd add a mask. You might add something about the the coordinate reference system. You might add other sort of domain-specific methods like for calculating integrals or derivatives or something. And like all this stuff you can kind of do in a very like type-safe fashion because you have these objects that propagate along. So that's my overview of Coordax.